Good afternoon, everyone. My name is Geng, currently the manager of Huawei Canada Computer Network and Protocol team. And it's my pleasure to present our work, Config-Snob, a data-driven network protocol tuning system today. So, web servers are deployed around the world, but often rely on default or predefined configurations. Okay? But the one-size-fits-all approach falls short in diverse network scenarios, and the static protocol tuning is not feasible. So here's why. First, clients are diverse based on factors like geolocation, ISP, and the network interface. As a result, they experience different network conditions, such as different bandwidth, different RTT, different packet loss rates, and which impact the performance and the effectiveness of protocol tuning. On the other hand, web server configurations involve numerous knobs or parameters with complex dependencies. So for example, here you can see the table, even for TCP, you have so many different parameters, like the initial window, like the pacing rate, and so on. So tuning them jointly is very challenging. In this presentation, we'll explore strategies to address these issues and optimize our web server performance. So let's delve deeper into a tailored solution. Here, the server receives numerous requests from different clients. The server has to set the best configurations for each request. To handle clients' diversity and network dynamicity, we introduce Config-Snob. This protocol tuning solution leverages historical data to select optimal configurations. So a protocol tuning solution poses several challenges. So let's compare the related work to see how our approach addresses the challenges. Here we compare the TCP RL, the TCP initial windows, and the congestion control schemes through reinforcement learning. And also the NSDI 22 configurator, a data-driven approach to improving seeding performance, which we think is the closest work to our work. So first, the protocol stack involves a large number of configurations, each with its own complexities. So our proposed black box solution jointly tunes the interdependent configuration knobs together. Actually, in fact, we consider in total 8 parameters, knobs, and specifically related to QUIC and BBR. Second, diverse clients and dynamic network conditions pose significant challenges. Here, Config-Snob addresses this by employing a two-level client grouping approach. Third, randomly selecting configurations leads to poor performance and typically suits a small and limited decision space. So existing approaches highly suffer from performance degradation in the exploration phase, impacting client connections. So clients cannot afford such poor performance, even for a few connections, before getting the optimal or near optimal. Here, Config-Snob uses a controlled exploration, which I will introduce later. Last but not least, the average reward is calculated to evaluate the impact of configurations, which may not be accurate due to randomness and complex dependencies between data samples, as well as insufficient data in some realistic scenarios. So here we design a reward estimator technique based on causal inference to provide an efficient and robust prediction of the impact of the changes of the configurations. Next, we will explore how Config-Snob enhances web server performance. So dealing with connection individually is impossible and usually leads to very few data samples. Also, one may think you can use like IP prefix. Actually, it's also can have the same issue, not overcome the shortage problem. Therefore, the main purpose of profiling is to achieve scalability. Initially, we use fixed features to group requests into profiles. Profile features such as geolocation, ISP, IP subnet, and the connection time. However, profiles may result in a smaller number of samples, which is suboptimal for training. So to address this, we use a clustering method to create profile groups characterized by similar network conditions. Therefore, we can allow for the joint training and address the scalability issue. Okay, let's go over the learning model. For training, Config-Snob uses a Bayesian optimization model, BO, as the learning model because it provides black box optimization that can adaptively explore the search space and find the best set of parameters. We use BO in the granularity of the profile group I just introduced before, and we use historical configuration performance to bootstrap the exploration from overlapping profiles. Then there is always a question, okay, about the trade-off between exploration and exploitation. Naturally, Config-Snob uses multi-arm bandit to handle the trade-off. So one arm is used to perform exploration when the profile group does not have enough samples, especially at the cold start phase. And at the steady state, the best predicted configuration is used. Then the question is how to handle the local optimal or overfitting. Here is always a challenge. Here, Config-Snob uses another arm during the steady state, which is the same BO model used at the cold start state. However, Config-Snob uses smaller step at this phase rather than the larger step in the cold start phase to continue the exploration to avoid the local optimal, but in a very conservative manner. But still, there is non-Gaussian noises. So to tackle non-Gaussian noises and further utilize recent history records, the last added BO model arm with a resampling mechanism. Here is used to do moderated exploration in the steady phase under specific conditions. Resampling in a steady state happens for each profile group only if the number of configurations tried or seen by the BO exploitation arm is greater than a threshold. This BO model is initialized with the top 5 configurations with largest rewards. Then it goes to the last questions or challenges to handle the inaccurate reward. The detailed reward function can be found in our paper. Here, I don't introduce the details. But the inaccurate reward mainly stems from the fluctuation within the same group. To solve this, we use a causal inference-based reward estimator. So before, let's go over briefly about what is causal inference. Causal inference, CI, is a statistical technique that allows us to find out the causal relationship between different problem variables. Of course, to identify the impact of a specific variable, here we call it treatment, and on an outcome. Also accounting for the influence of other variables, here we refer to as co-founder and covariance. Config-Snob uses CI to precisely estimate rewards and to ensure that the selected configurations for new connection are less prone to negative experiences. So by predicting the impacts of the changes in the configurations, by using CI among different network conditions, the CI-based reward estimator can improve the accuracy of the calculated reward. Moreover, CI is utilized to refine the search space by excluding the configurations that have bad impact to the performance for sure. Putting all together, the design overview of Config-Snob is shown here. First, client requests are received. Then, based on the extracted profile information, Config-Snob set the associated configurations. We build a module to collect all the data, such as unassigned config, profiles, network conditions, and rewards, and send it to the training server periodically. At the training server, we first apply our grouping approach, have the different clustering. Then we train the MAB models of each profile group, and the causal inference functions are used. Finally, the best configurations are generated and sent to the application server. So more details about the design, especially about the causal inference, can be found in the paper, also about some deployment details. We deploy Config-Snob in a large-scale production environment of video service application. The solution is deployed in two regions, namely Turkey and Philippines. In Turkey, it serves 3 edge nodes with 140K user requests per hour, like 3 million per day. And also 1 edge server in Philippines with 800K user requests per hour, like 19 million per day. Config-Snob test data was for more than 1 month. And we also configured the servers to keep using the default configuration for like 20% of user requests for a good comparison. So Config-Snob improved the completion time for video sessions over the default configurations by 36% mean and 70% median for Philippine servers, and 15% mean and 62% median for Turkey servers. So Turkey servers experience worse network conditions than the Philippine servers. That's why we can see the solution converges better prediction and in Philippines leading to better performance. For 10% completion time improvement, Config-Snob has like 1.8% for Philippine servers, however, has this negative 8.9% for Turkey, therefore not always positive improvement. In general, we analyze these performance degradation cases, which occur mostly due to harsh network conditions for some connections with very high loss rates. Also, Config-Snob achieve higher goodput in both regions. We also use a trace-driven testbed to compare Config-Snob with some existing work, like the cherry pick and the configurator. All experiments are quick sessions over simulated network tunnels. We use mahi-mahi. So Config-Snob improved the completion time by 49% mean and 55% median over the default configurations. We can see the cherry pick result into slightly poor performance due to random exploration. And for configurator, the decision tree actually improved the result when used in place of BO at a steady state, but it used random initials for exploration. Config-Snob shows significant improvement due to the MAB model, two-level profiling, and the controlled exploration that starts with prior knowledge initials. To conclude, Config-Snob a data-driven solution to find the best configurations for the diverse network environment, which uses like multi-arm bandit and a causal inference model and the 2-level of client grouping. Our solution is not general, but adaptation can be applied to different networking protocol stacks like TCP, QUIC, HTTP, and different services like web, video, and so on. In our future work, we aim to extend our design to tune the online parameters. Here is just the initial parameters. And online, like the BBR kind of congestion control related parameters, is in our future work. And also, we find that causal inference techniques show great potential to overcome some of the optimization tools issues, which are also part of our future work. Yeah, that's all. Thank you. I'm happy to take any questions you may have.